So we're still going to be having a set called A, and R is a relation on A. And we say R is symmetric if whenever A comma B is in R, we also have B comma A is in R. So in other words, you need to be able to flip the coordinate and still have it be at. So let's look at our division relation. Is our division relation symmetric? If x divides y, does it also mean that y divides x? What about x less than y, this less than relation? Not symmetric, why not? And so to say it's not symmetric, all we need is one example. Make it concrete, let's just say 2, 3 is in L, but 3, 2 is not in L. So this is sufficient to say not symmetric. Not equal, the pairs of integers that are not equal to each other. Is it symmetric? Yeah, it's symmetric. And let's write out a formal proof. So suppose xy is in not equal. Then by definition of not equal, what does that mean? We have x is not equal to y. It follows immediately that y is not equal to x. So for the level of proof that I'm writing as a beginner, I want to beat this point over the head and show exactly what the definition was. Since yx is in not eq whenever xy is in not eq, we have that not eq is a symmetric relation by definition. You really don't want to leave your reader any especially when they're starting out. You want to write down every line, and that's for the reader's benefit, but it's also for your benefit so that you're 100% certain on what you've shown. Sorry about that. Definition. Yes, that was not at all visible. There is one more property of relation that I need to tell you about, and it's kind of what it sounds like. So we're still going to be working in the situation where we have a set and a relation on that set. Transitive if whenever we have A and B in R, and we have B, C in R, we also have AC. I want to look at this relation that we defined on the set S, this finite relation of 0, 0, 1, 1, and 0, 2. And I want to ask you, is this transitive? Turns out it is, because there's only one pair that we would have to check. That's 0, 0, and 0, 2. And if you look at the definition here, 0, 0 would be like our AB, and 0, 2 would be like our BC. And we do have our AC, which would be 0, 2 in the relation. What about this not eq? I really like that example. Thank you to whoever came up with it. Y'all have been coming up with some really nice examples. This not eq relation. Okay, and the answer is no. So let's look at 2, 3 is in not eq. Do you agree? And 3, 2 is also in not eq. Do you agree? So this is like my AB in the definition, and this is like my BC in the definition. Is 2, 2 and not eq. You can't, if you think about it as a graph, what it says is that you have to be able to take shortcuts, and there should be any path that you can take, you should be able to get in a single. So this means that this is symmetric. In fact, there's an arrow from 2 to 3 and an arrow from 3 to 2, but there's no loop. There would need to be a loop here because I can get from 2 back to 2 in 2 steps. If it's transitive, I need to be able to get from 2 to 2 in 1 step, and I can't. So let's look at another one. What about divides? Is divides transitive? How about y'all take a minute and think about it? So it's gotten us started. What we want to do is we want to start out supposing that AB and BC are pairs that are in a relation. And at the end of it, we got to do our work here. But then at the end of it, what we need to conclude is that thus AC is an element of D. And this is where our work comes in. But because AB is in this relation, A divides B, right? That's the definition of the relation. And BC is in the relation, so B divides C. So now I need to use my definition of divides for integers. So there exists P and Q in Z such that what? Such that A times T is equal to B and B times Q is equal to C by definition of divides. Now there's still this gap. We're not done. I put the end at already, yes. So B times Q is equal to C. What can you replace B with? AT, right? So then this means that C equals B times Q is equal to A times T times Q. And let's write the A as a special emphasis here. So A times TQ. This A and Q weren't the best choice to go together. I'm trying to make Q have a really long tail. And that means that there exists an integer T times Q, so that A times T times Q equals C. Because the product of two integers is an integer. There exists TQ and Z such that C equals A times TQ. So A divides C. That's the definition. And since A divides C, AC is in this D relation. It does it because what we wanted to prove was that if A, B, and BC were elements, then AC also had to be an element. And we started with our hypothesis and we did the work until we were able to conclude our conclusion.